achieving high throughput and good performance with a few clients is actually pretty easy. Where it gets really complicated and really important to differentiate systems is in a large network, multiple clients, multiple access points. When you have that, you need to have a system that can better manage client activity. You'll find that the problem is you can have a great infrastructure, but if it doesn't accommodate the way clients behave, you can have a pretty big problem. For example, band steering. That's a solution to a problem of how do you handle dual band access points. Client load balancing, making sure the APs are being adequately used among your entire system. And airtime fairness, making sure those legacy devices don't slow down that brand new 11N system you just purchased. Band steering is pretty simple. You have an access point that is dual band. Now I always recommend that you buy dual band access points. That means it's got two radios built in, a 2.4 gigahertz radio and a 5 gigahertz radio. It's like two APs in one box. And what you get with that is basically two networks, a 2.4 and 5 gigahertz. The advantage is you get a lot more channels. If you remember from other segments, a 5 gigahertz network has a lot more channels to choose from as compared to 2.4, which typically only has 3 channels. So you want all the traffic you can on the 5 gigahertz network. Now what typically restricts that is two things. Number one, the client. Your client devices need to be dual band to really get what's best and what's necessary for a dual band network. If you have a dual band access point, but all of your client devices are 2.4 gigahertz only, then it didn't make much sense to buy those dual band APs. Dual band clients can be had. They're really not that much more expensive. The Apple iPad, all the versions of the iPad are 5 gigahertz and 2.4, so they're dual band. When you buy a laptop, you can request and upgrade a chipset to dual band for actually very little cost. But even once you do that, systems tend to always run home to 2.4 gigahertz. Client devices, even if they have a 5 gigahertz option, don't always choose it. So what Ruckus has done is it has a system called band steering. When a client device is connecting, it has to send out something called probe request frames. Well, if a Ruckus system sees those probe request frames on 5 gigahertz as well as 2.4, we know it's a dual band system. It's a dual band client. So what we'll do is the next time it connects, because you don't want to disconnect something to move it, so the next time it connects or roams, we will steer the client to 5 gigahertz. And the way we do that is we make 5 gigahertz more enticing. We'll give it a faster probe response. So we'll send back a probe response frame faster from 5 gigahertz and kind of hold it back on 2.4. It does take into account signal strength. So if an AP doesn't see a client with good signal strength on 5 gigahertz, it's not going to steer it that way. The end result is much better performance. You're taking your clients like this. Let's say we have, in this example, 17 different clients, and three of them connected to 5 gigahertz just randomly. With band steering, you can take that same number and get more of them to connect on 5 gigahertz. The advantage to that is you're using those dual band APs with much more channel, much less noise on 5 gigahertz. Overall performance is dramatically improved with band steering enabled, which it is by default. You don't have to do anything to make that happen. Client load balancing. Another issue is clients don't actually make the right choices. We learned that they don't make the right choice when it comes to 2.4 versus 5 gigahertz, and they also don't make the right choice when it comes to which AP to connect to. When a client boots up and the client is searching for an access point, most of them don't go through anything really dramatic. What they do is they say, which AP is out there and which has really good signal? Maybe I'll attach to the first one I hear. If you have a client here in the middle of these 3 access points, probably what you want is it to connect to the AP with the least usage. Now again, a client won't take that into account, so we have to steer it to do that. We want it to balance. So if the client is here and we have 3 access points that it can hear, then what we'll do is if this client over here, this AP over here is used less, let's say it just has fewer clients and less traffic, then this will send out probe responses first, a lot like the 5 gigahertz and 2.4 band steering. We'll make this AP more enticing to that client and try to get them to connect. The advantage in the end is clients are balanced on channel. So they're balanced among the multiple APs that you have, because in other situations, if you let it just free reign, you'll find that they may all connect to this one and one or two on these two, just randomly. There's no real science to it. It's just kind of who got there first. So client load balancing is a very important feature, again, enabled by default. One of the more complicated problems to explain is that of 11N and legacy devices. 802.11n is fully backwards compatible with 802.11 original, B, G, and A. The problem is that the way Wi-Fi contention works is a very fair system. So if I'm trying to, if you and I are going to have a conversation, I'll talk and then you talk, and we go back and forth, and that's how conversations occur. The problem with this is that if I talk really fast, like an auctioneer, and you talk really slow, oddly enough, we're actually saying the same amount of data. Here's an example. Let's say you have a small one-lane animal bridge over the river. You've got 10 turtles on one side and 10 rabbits on the other. When you have, since they're going to take turns, the turtle goes across, and it may take 10 minutes for that turtle to get to the other side. And then the rabbit goes really fast. And then they go back and forth. Even though the turtle is very slow, which side wins? Well, the answer is it's equal. So the problem you'll see is when you have 11N device and a legacy client device at the same time, and they're both moving a lot of data, surprisingly, the amount of data they move is exactly the same. Because even though the 11N or the rabbit can move much faster, it's still taking turns with this really slow device. So if you add up back and forth, you'll find that it's exactly the same. That's where the solution lies, is now let's make it more fair for time. Let's say, since the turtle takes 10 minutes to get across, we'll say, all right, turtle, you get 10 minutes to go across, and then we'll give the rabbits 10 minutes. Well, the rabbits are going to bust right through because they're so much faster. So now we're making it fair, not by one for you and one for you, we're making it fair in an amount of time. So if we say, all right, the amount of time a legacy 11B device took to send a frame is 100 microseconds. Well, now let's give 11N 100 microseconds, in which case it could maybe send 15 frames of data as opposed to 1 with 802.11b. The results that you'll see is a significant difference in throughput. 11N being much faster than 11B, like it should. But if that doesn't exist and they sit there and take turns like you see here, your throughput is going to be exactly the same. And you'll wonder why your brand new 11N system isn't any faster than your legacy device. So this is a good set of features, client load balancing, airtime fairness, band steering, that all make up managing client devices, both legacy and new, to make sure that we always get the maximum amount of throughput and performance that our Wi-Fi network can handle.